Okay, so now I have connected it together. As I set here in at the middle of the potentiometer, which is here on the schema, I will pick up the audio signal, and the white alligator clip is connected to it, and it is here connected to the input of our audio amplifier. It is connected to pin 3, so that was our schema for it. So it is connected to 3, and the audio amplifier is wired with the components you can see here. So that is what we have on board. Our power supply is already connected with close to 12 volt, so that is what we want to. And the grounds are interconnected, so everything is ready. My RF generator, which is simulating the TX power with minus 10 dBm, so that is the input power, and that will be the input power available at the mixer input. Here is our little mixer. That will be the level which is available when I'm testing a radio with 100 watt, because as I told you before, 100 watt is plus 50 dBm, and I have an attenuator in between which is attenuating this 50 dBm by 40 dB, and then I have a second little, not the huge one, which have to take really the power, but I have a little one here. This is again a 20 dB attenuator, so I have 60 altogether, and yeah, simple, plus 50 dBm, which represents 100 watt, attenuated by 60 dB means when I'm testing a radio, I will have at this connector, so that will be the connector then, I will have minus 10 dBm, and minus 10 dBm is now represented by my signal generator, and as well with 14,001 megahertz. So, okay, everything is connected, so the only thing which is not switched on is my local oscillator. So my wave station is still not switched on, and I will do that now. Aha! So, look at this. Here is the potentiometer, and I can adjust the volume, and as we said before, what we want to have at least are 50 milliwatt, and we made here a little calculation with 700 milliwatt at the output. This will be 61 milliwatt. So what we're gonna check now is if we are turning on the level, we will check if we are available to reach our minimum 700 millivolt, and we have here the indication, and for the moment in time we have 60 millivolt, and you still can hear the tone. And now watch the signal itself and the level. So I'm increasing now the level. Okay. So we are really able to reach 700 millivolt and a bit more. So that is very, very promising. So from the perspective, for the time being, our idea seems to work as it should. So that is pretty nice. So what we need to check as well, so maybe we can perform as well a little total harmonic distortion test. So therefore I switch on my THD tester and I connect my coax cable to it. Now I have to install this T adapter that I can have at one side my oscilloscope, and at the other side I connect my distortion meter. So that is now installed, and now I'm gonna increase the level to, I increase it to 700 millivolt. Okay, I must take it down. My adjustments are not perfect, so I still have the indications here that frequency setting is not correct. So first of all I have to adjust here my settings, and then we can measure the distortion level. Okay, adjustments are done, so the distortion analyzer is connected and is reporting 3.8%, so that is not too bad. I will not really complain on it. So the only thing is I just want to check if I put it directly into the analyzer, what does it mean? Yeah, it is around 3.8, yeah, getting to 4%, so that is basically not too bad, considering that we are really here on the breadboard, and So everything is with we call it flying wires, and so therefore I'm not really complaining. So that is basically okay with a level of about 700 millivolt. So let's double check with this one. Yeah, so he's also reporting nearly 700 millivolt. And what is he reporting on distortion? Yeah, it's nearly the same. So it is reporting as well. Yeah, close under 4%. So that is pretty nice, and the sinus is okay. So I'm sure we will improve the signal distortion when we have all on a real PCB. So that will be next. I will build it on a PCB, and then we will check how it works on a PCB. But up to now, we can say we are really on the right track, and yeah, it seems to become a nice little lab device, which will hopefully very handy. Okay, so we are moving forward. I have almost done my circuit board planning. So that is so that will be the circuit board for the audio amplifier, and yeah, it will look a bit like this here. So I'm using this proto boards. So that is yeah, it is not a big deal to do this small amplifier. So I have less components, and so it doesn't really make sense to produce a printed circuit board. I think this proto board will do the job, and yeah, therefore you have to do the planning, and that is what you see here. So the IC and the capacitors, the resistors, and whatever. Here we have a voltage regulator, which will sit here, as you can see. And yeah, I gonna start soldering it, and afterwards we can check if it works. Additional to that, I found in my stock a little transformer. So it is a linear transformer, and it is putting out 17 volt. This regulator is a 12 volt regulator, so that will then exactly fit on what we have tested here on the breadboard. Yeah, and so we are going forward, and let's see when it is finally soldered how it will work. Okay, the power regulator is already on board, and it is connected right now to the power supply. this main socket power supply, and is connected here to the input pins, and at the input we have currently 16.8 volt, so that is the input, and that is an 12 volt regulator with the capacitors connected to it. And on the output, so the output is connected to my electronic load, and you can read here the voltage at the output. So the output voltage is 12 volt. So that is what the regulator should do. So from this point it is working. So now, but there is no load connected to it right now, so it is still switched off. I have chosen 100 milliamp because that is a nice power to test how the regulator works, and this kind of regulator housing, the TO220, is designed to take one or to deliver 1 amp, but normally with the heatsink. But looking back into my data sheet of the LM386, we find here low current drain, so 4 milliamp only. So that is really an amplifier for battery operation. So if this circuit is finally working with 100 milliamps, then everything should okay. So then we can be sure that it will definitely work with 4 milliamps as well. So okay, let's switch on. So load switched on right now, and you can now read. So that is the current which is drawn, and that is 1.2 watt. Our output voltage is still 12 volt, so that is fine, and input voltage is 15.3. So that is quite nice. Everything is working. So I just want to check the temperature, the typical finger probe, you know. So yeah, with 100 milliamp, you do not really need to put the heatsink to it, and as we see in the datasheet, it's only 4 milliamps, or let it be 10 milliamps, what will be drawn by the amplifier itself. So you know, that is at least nothing for this power supply and for this regulator. So that is clearly oversized. So that is clearly oversized. I could have taken a smaller regulator as well, but you know, so there is now some reserve, so which is not bad at all. Then secondly, I'm just connecting the oscilloscope to it, and that is now measured in AC, and we have yeah, so that is what is it? Let it be maximum 800. Oh, that is microvolt. So that is microvolt. So it is adjusted in the 2 millivolt per division, and yeah, so that is the noise on it. Now I can switch it to. Let me switch it to DC. Now it is DC coupled, and let it put to 5 volt per division, and let's check once again. Yeah, you can see the reading is 12.3, and yeah, ripple is quite low, which we have measured in AC mode, and so yeah, we can say this is okay. I'm still checking the temperature. I recognize that it is heating up, but as you can see, it is no problem to leave to let my fingers to leave it on the regulator. So that means the temperature is below 50 or 60 degrees. So what is it? Below 50. I guess I could measure it, but that is not necessary. So I'm sure. So I'm still drawing 100 milliamps, 1.2 watt. So it is still working. And yes, you can feel it's getting warm, but no problem at all. No problem at all. I can leave it as it is, and I will finish now with the amplifier itself. So I just wanted to make sure that the regulator is working before I put the other components on the board, and yeah, so far this test is okay. Okay, our amplifier board is ready so far, and now we have to perform the final test. So I have already connected the signal generator with 1 kilohertz to the input. Then our power supply is connected to the circuit with 15 volts. As you remember, we have here our voltage regulator, which will keep it on 12 volt DC. And finally, this here are the leads to the loudspeaker. So I really want to leave it on the speaker, and I put it around that it is not that loud. And to the loudspeaker I've connected our oscilloscope just to check how the signal look like. Okay, so I start with 1 millivolt at the input. So we have 1 millivolt at the input, and it is switched off for the moment in time. So let's switch it on, and what we want to see at the output with a load of 8 ohms, so that is the speaker at least, we will see a sign with 650 700 milliwatt, because that would represent approximately 60 milliwatt, and yeah, that was our requirement. Okay, so shall we go? Okay, switch it on. Okay, so you can already hear a tone from the speaker, and we see a small sign on the scope. Okay, so then we will increase the output of the signal gen, that we have at least 700 millivolt at the output. Yeah, 650. Let it be at 650, and yeah, the tone is annoying, but I want to leave it at the speaker, because what we want to check as well is the distortion, and yeah, what you can see, it is a nice sign, and now I connect it to the distortion analyzer. Okay, so put it into the distortion analyzer, and the analyzer is regulating, and what you can see so far is that we are very low, and so I can go to 3, so 3% is now scale end, so we are at 5, so that means 0.5, so I can go to 1%, so it's adjusting, and what can we see? 1% is scale end, and we are at 0.53%. So that is very low. So let me switch it off. So that is really annoying. If we go back to our data, we find that it is a low distortion type, which will have at least 0.2% of total harmonic distortion, with a gain of 20 and a supply voltage of 6 volt at 8 ohm load resistor. So okay, we have 0.5, that is what we measured, 0.5%, but we are running the amp at 12 volt DC, and that is what I wanted to have, because with a higher supply voltage we can reach a higher output gain, and yeah, our requirement was at least a minimum 50 milliwatt, and we easily reach our output requirement, and secondly, we are reaching a very good value for total harmonic distortion and noise, so 0.5% is a very good value. Remember, on the breadboard we were only able to reach, yeah, best case was 2 or 2.5%, and I already guessed that we will be reaching a better level when it is on a board, and so that is what finally happens. We are now really getting a better output value, and you know, 0.5 maybe that it is not the real value, because I'm using a normal signal generator to feed the amplifier, and normally what you need to do if you want to check an audio amplifier and you really want to check the THD level, you need a low noise oscillator, so something like this here. So this is a low distortion and low noise sine generator, especially for THD measurement, because you simply can imagine if your signal generator has at least a very high total distortion, harmonic distortion, then it is clear that your amplifier will amplify this distortion level as well. So if you really want to perform a distortion measurement, you need to feed your circuit, your amplifier, with a low distortion sign, and therefore you need really high value equipment like this HP low distortion oscillator. So that is 239A, HP 239A oscillator, and yeah, if you're interested, you can watch the data of this signal generator, and you find that it is a true low distortion generator for yeah, finally for distortion measurement, and yeah, for audio equipment and whatever, but that is a different story. Okay, so our amplifier is ready. Now I'm switching these units together, and then we will have a look if it works together with our mixer circuit, which is down here. Okay. Okay, both circuits are connected together and up and running, and currently I'm measuring the distortion level, and what you can see here, we are on a 3% scale end, and so that means this scale is valid, so that means 3%, and we are now in the complete circuit at a dip under 0.9% THD, so I wouldn't complain on that, so that is okay. If I bring it back into the oscilloscope, you can see a nice and clean sine with 664 millivolt, so that is absolutely great. Everything is working, so I'm quite happy so far, and yeah, maybe that I will improve the THD level at least a bit, because again we have flying wires here, so that is not good, at all. Yeah, but that will be completely different when I put it in the box. Yeah, next will be starting with the housing, because everything is good with the circuitry, and I can start with the housing right now. So mechanical work has to be done, so I'm currently cutting out the new front panel, which fits into this housing here, and that is what I'm currently doing, and then I have to think about how to lay it out, that I get all the front panel switches and BNCs and what have you onto it. So yeah, that will be next. Okay, so far new front panel is ready. So now I have to think a little bit about how to lay it out, how to design it. And currently, yeah, I have an idea on what we could do so far, and yeah, I need to put the BNCs and all the switches and what have you, and at least the speaker, which should go here in the upper corner, and yeah, some measure BNC outputs and such. So yeah, next will be to order the switches, because the switches I need I do not really have on stock, so I need to order them, to order these switches, and then yeah, then I will finally start drilling all the holes which I need to put all the stuff into the front panel. So yeah, ordering will be next, and then we see what we can do on preparing the mechanical yeah, design, whatever. Okay, so far. Okay, metalwork is almost ready. So holes are drilled. Here is one left. Now it needs to get polished a bit, and yeah, then we have to install the switches and sockets and what have you, and then we can go ahead with the circuit. Speaker is in, so let's go ahead. Okay, all switches and sockets are installed, so everything is in place. So we now have to fit in the circuit, and then we can start with the wiring, so that will be next. Currently I'm preparing the wiring which we need to get all the connections to the front panel, and now I can put the little PCBs into the housing, and then I can start to connect all the wires to the front panel to get it in operation. Okay, circuit is already in the housing. So wiring is prepared, so we can start connect the wiring to all the switches and pots and yeah, what have you. So we are making progress. Yeah, step by step we moving forward. So first wires are soldered and we are going ahead. Okay, the wiring is almost done. So what we have to do later on is to connect here and yeah, down there the capacitors and resistors for the different gain settings for the amplifier. For the moment in time it is fixed on 20, so the gain is 20, but to have different gain settings I will set later on different gain capacitors to set the different presets. And the dummy resistor is down here, so maybe you can see it better like this. So this is an 8 ohm dummy resistor, so that we can switch between the speaker and the dummy, and therefore we have this switch at the front panel to switch between dummy and speaker, and this is the measure output, which is directly connected to either the speaker or the dummy, so I can get the measurement from the audio frequency. So that is very needful to yeah, use it for different purposes. Yeah, so the RF coax cable are also connected for the local oscillator and the RF input. And so now I have to connect ground and supply voltage to the back panel. So this is the back panel, and there is already our DC jack for this little transformer, so we can supply the circuit with the little transformer, and then our voltage regulator is on the board. As you know, when we designed the board, you know that we have a regulator down there, so all the voltages are regulated to the voltage we need for our RF, for our audio frequency amplifier. Okay, so let's go ahead. Yeah, and that is the back panel, basically with the DC connector for our supply, and yeah, supplying the circuitry and yeah, all what we have. Front panel is already in place, as you can see, and we have really nice access from the back panel to the circuitry if we need to. So well, as I said before, this housing might be too big, but anyway, for the front panel it is nice to have all this space to can operate it nicely. So, well, it doesn't matter that the housing is maybe a bit too large for this small circuit, but anyway, so I like it. So everything is prepared for testing. So I have set up my local oscillator input, which we had on 14 megahertz, and as RF input, as we tested it before, we have 14001. So that is the 1 kilohertz we want to win back as audio signal, which is going into the RF input. Okay, so let's switch it on. Okay, unit is on, so this is indicating that the amplifier is switched to DC voltage, but my local oscillator needs to switch on, so that is on 7 dBm, and we switch it on, and listen to that. Very nice. Very nice output signal. Okay, so let's check what it is in terms of signal strengths. This is our measuring output, as I said before, and we can now connect the output to the RF input, audio frequency input. Okay, so now we are on 263 millivolt. Let's check what the sine would be. It is 42, very nice. And what is the audio distortion? So it is under 1%. It is 0.7, which is great. Let's check how the signal looks like. Here we are. We can do it a bit bigger. So look at this, very nice and clean signal, which is confirmed by the distortion. And now, by the distortion level, right? So now we can switch it to the internal dummy load. So that is more useful for measuring purposes. So now it is switched to the internal dummy, and we have the signal here in the set still available, still with 0.7% THD, which is perfect. So that is really great, and a very, very clean sinus, so that is really nice. And finally, let's check when I go back to level, so 0.6. So when I now increase the level, audio level, to 600, which we would like to see. Yeah, look at this. So we reach easily our 50 milliwatt audio output signal, which we really wanted to get. And the tone you are hearing right now is generated here from the internal amplifier, and I can put it down as well. So here we are on the dummy, as I described. I can switch it back. So that is what we have, and I can switch it back to dummy resistor, and I have here all my measurements I wanted to have. Look at this nice and clean sign. So that is really nice. Okay, so finally project is finally finished. So this is the input, the external input, and then I can switch it to external. I have to add the different gain values, which can be switched by this switch. So that is still to do. I need to put some informations here on the front, which switch is which, and and I need to put a nice knob here to the pot, and then project is done, and as you see, it is working right. It is working as it should, so that is what we expected. And I'm really satisfied with what we have, and let me do the final steps, and then you can find this set in future videos, always in operation. Okay, lab monitor is ready to go, and I will be testing with a radio here. So let's try. 1 2 3 1 2 3 test. 1 2 3 test. 1 1 1. Okay. 1 2 3 test. Test. Yeah, so you see, it is working, and this project is done, and hope you enjoyed it a bit, and catch you next time.